Welcome to The Explainer. I want you to look around you right now. Over 90% of the items in your room, your furniture, your electronics, maybe even the clothes you're wearing, likely arrived on a massive cargo ship. It's amazing, right? But that convenience comes at a really heavy environmental cost. So today we are tackling one of the most complex, massive, and frankly fascinating engineering challenges of our time: decarbonizing the global shipping industry. The industry is under immense pressure to clean up its act. And while some are looking at entirely new fuels, others are exploring a radical technological solution, which is basically capturing the carbon right out of the exhaust before it even has a chance to hit the atmosphere.
Okay, let's dive into this. We've got a lot of ground to cover today. We are going to explore the sheer scale of the emission problem, corporate policies, the really complex chemistry behind carbon capture, the logistics of actually making it work, and finally some environmental critiques. It's going to be a great journey.
Let's start by framing just how massive this shipping emissions problem really is.
50%. The International Maritime Organization, or the IMO, has basically drawn a line in the sand. They've mandated a target to reduce greenhouse gas emissions from international shipping by at least 50% by the year 2050, compared to 2008 levels. And the broader ambition? To hit net zero emissions around that same 2050 mark. This is an incredibly aggressive target. I mean, to put this into perspective for you, a single large container ship can burn up to 63,000 gallons of heavy marine fuel in just one day. Achieving a 50% cut means the entire global fleet has to completely reinvent itself over the next couple of decades.
So, how do major industry players actually respond to a mandate that massive? We're going to look at Evergreen's Green Fleet Strategy. We're using Evergreen Marine Corporation as our primary case study to see exactly how global policy translates into actual corporate action. If you look at Evergreen's corporate timeline, it's designed to map directly onto and actually accelerate way ahead of those international regulatory targets. While the IMO set the 50% reduction for 2050, Evergreen is aiming to achieve that same 50% reduction by 2030. And by 2050, their target is to be fully carbon neutral. And this brilliantly illustrates how multiple small efficiency gains compound over time. To hit these aggressive milestones, Evergreen is doing a bunch of different things. They're slowing down their ship speeds, a practice called slow steaming, which drastically cuts fuel burn. They're using real-time weather routing to avoid storms and optimize their paths. They are even applying special anti-fouling paint to the ship hulls just to reduce drag in the water. But they are also making massive capital investments. For example, they recently ordered 10 new 15,000 TEU container ships powered by dual-fuel methanol engines. These are highly efficient vessels built specifically for the vital Asia-Europe trade lanes.
All right, let's pivot from those operational efficiencies to the onboard carbon capture technology itself. What we are talking about here is literally human ingenuity fighting against the laws of physics. Instead of letting the byproduct of combustion escape into the sky, engineers are trying to figure out how to grab it right out of the smokestack while a massive ship is moving across the open ocean.
Let's define this clearly so we're all on the same page. Onboard carbon capture and storage, or OCCS, acts a lot like a heavy-duty vacuum filter. Think about it. It catches the dirt, which in this case is the carbon dioxide, before it gets out. But just like a vacuum with a super thick filter, the machine has to work much, much harder to push the air through it. Right now, OCCS is viewed as a crucial transitional technology. It allows the shipping industry to keep using current fuels and engines while actively bringing emissions down, basically buying us time while we wait for true zero-carbon fuels to become scalable and affordable. But there is a serious trade-off here. While chemical absorption has an incredibly impressive capture rate, trapping anywhere between 30% and 90% of a ship's CO2 emissions, it comes with a harsh energy penalty. Running this capture system consumes 9% to 30% of the ship's total energy. Why? Because it requires intense heat to regenerate the chemical solvents that are used in the capture process. So, ironically, the system uses up a significant portion of the very fuel it is trying to clean. Which naturally brings us to the actual costs of carbon capture. Installing massive chemical plants onto moving ships is no small feat. Now, what's really interesting about this slide is how it breaks down the physical realities based on a detailed study by the European Maritime Safety Agency. OCCS suitability varies wildly depending on the type of vessel. A massive Suezmax tanker? It has plenty of deck space, so it's highly favorable with minimal cargo loss. But for a 15,000 TEU container ship, installing this equipment means you are physically losing about 175 container slots. That's a 1 to 3% hit to revenue right off the top. And for a RoPax passenger and vehicle ferry, it's incredibly challenging. You're losing about 100 vehicle spaces, and you have to navigate incredibly strict safety limits because of the tight space constraints and the chemicals involved. And speaking of those chemicals, this absorption process relies on liquid solvents like MEA, DEA, and MDEA. And these aren't simple, benign substances. They degrade over time, they require regular replacement, and their byproducts actually pose real environmental and safety concerns for the crew on board. But here's the thing, we know the technology actually works. Evergreen partnered with the Shanghai Marine Diesel Engine Research Institute and successfully piloted this exact system on their 13,800 TEU vessel, the Evertop. The results? Stunning. The pilot achieved an incredible 99.9% CO2 capture purity. So the science is totally sound. The real challenge is dealing with the physical footprint and the daily operations. Now, let's shift our focus from the ship to the shore, because capturing the carbon is honestly only half the battle. If you capture all this carbon on board, you can't just leave it there forever, right? You have to walk it through an entirely new supply chain. First, you capture and liquefy the CO2 on board the vessel. Second, you store it in specialized pressurized tanks, which, as we discussed, take up a lot of valuable room. Third, when that ship finally docks, it has to offload that liquefied CO2. And here is the massive bottleneck. The port must have compatible terminal infrastructure ready to receive it. Finally, step 4, that carbon must be transported and either permanently stored deep underground or utilized by another industry. Without a fully integrated carbon capture utilization and storage network at major ports worldwide, OCCS simply cannot succeed.
So, time for a reality check on where this all leaves us for the future.
We need to look at how environmental watchdogs evaluate these efforts. In the 2023 Ship at Zero report card, which grades the decarbonization efforts of major shipping companies, Evergreen Marine received a score of 39.5 out of 100. According to their grading metric, that equates to an F grade.
To understand why they got that score, we need to look at a core critique directly from the report summary. It states, and I quote, "The transition relies too heavily on scrubbers, which turn air pollution into ocean pollution, and carbon offsets lacking a commitment to absolute zero-emission fuels by 2030. Environmentalists make the argument that current corporate strategies rely way too much on extended timelines and offsets, rather than committing to immediate, absolute emission reductions. Breaking down their specific critiques, they point out that those exhaust scrubbers dump acidic wastewater straight into the oceans. They argue that 2050 targets are just too far away to prevent severe climate impacts today, and they're demanding much better data disclosure for other dangerous pollutants, like particulate matter and nitrogen oxides. So the crucial point is their recommendation. Watchdogs want to see shipping companies completely skip transitional fuels like LNG, invest directly into zero-emission fuels right now, and actively develop pure green shipping corridors. So bringing it all together for this explainer, onboard carbon capture is positioned as a necessary but highly complex technological bridge. Shipping companies are walking a really dangerous tightrope here. They're trying to keep the massive machine of global trade moving profitably while simultaneously waiting for true zero-carbon fuels to mature and actually become available worldwide. OCCS might be the exact patch we need right now, but it's going to require massive, massive investments in both ship modifications and port infrastructure. Which leaves us with this final provocative thought. Can human engineering and carbon capture technology scale up fast enough to outpace the massive, ever-growing demand for global shipping? It really is a race against time, physics, and economics. Thank you so much for joining me on this explainer. I hope it helped bring some clarity to a deeply complex topic.